This is a lesson on the basics of current in the unit on circuits. So as we head towards circuit analysis, I wanted to give a good foundation of what current is so that's not troubling you as you move through circuit analysis. So here's the larger properties of current that I gathered together. Circuits must be closed for current to flow. That is a big principle. I have a few examples of that to go over. But when you're looking at circuits, really think about if there's current in a branch. If there's no current, if the circuit isn't closed, then current won't flow and you won't have to worry about that branch. Charges move according to electric potential, so we've seen that in prior lessons. Positive charges move from high to low, and negative charges move from low to high. So when we apply a voltage, so if I put the symbol for a battery in here, and you may have just a single long plate and short plate, which there's the plus and minus plates. The high voltage is over here, and the low voltage is over here. Another way to symbolize a voltage is with multiple plates. There are also different types of power supplies. These are DC batteries or DC voltage supplies. If you have an AC, it will look something like this with a sine curve in it. That's alternating current. So direct current means that the current flows in one direction. Alternating current obviously means that the current alternates directions. So in most circuits that you will work with at introductory level, we'll look at just the direct current effects on a circuit element, because some of them, when you put an alternating current through it, they have different effects. So we'll hold off on explaining too much about that there. But the alternating current is what comes out of the wall for electricity for us. And DC is most simple batteries. Another thing I'm going to remind you is that charges will always move freely inside of a conductor. And by a conductor with circuits, we mean a wire. In these situations, we're going to assume that the wires offer no resistance. The only resistance we'll look at is of the resistors that we place in the circuits. So, all along a wire, a charge is free to move. And another thing that means is all along a wire, it's an equipotential line. And we saw that when we talked about equipotential lines and work and energy. It takes no work to move along an equipotential line, so those charges will move freely in wires. So we'll focus on circuit elements and what effects those have on the circuits. Current will always follow the path of least resistance, so we'll see that in different applications when we add resistors, but also when we add different types of circuit elements, capacitors and inductors. Finally, something that you may have feelings about, I'm okay if you have feelings about this, conventional current is defined to be the direction in which positive charge flows. And up until this point, I have been very explicit in saying that negative charges, the electrons, are the ones that carry charge in conductors. The protons and positive charges are bound to their atoms, and those can't move. So unless you have a liquid with ions, positive ions, where the positive ions are the charge moving, electrons are typically what's going to cause current, especially in wires. We're working with metal. They have lots of free electrons that aren't bound to the potential of the atoms well, and so the electrons are what are going to move in the wires. But conventional current is the direction in which positive charge flows. And the reason for the convention is because they figured out current, physicists, long ago, you can imagine them in your head, long ago, physicists figured out current and how to get current to work before they figured out positive and negative charges in the atom. They had no clue how an atom worked, but they could get circuits to work. So at the time, they defined, and it made a lot of sense to them, that current was the flow of positive charge. Okay, so the electrons are the actual charges moving, but as I move forward, I will look at the direction of positive charge flow in circuits, and that is by convention. Okay, so yes, have feelings about this. This is wrong. And also, as we analyze circuits, we are going to think about positive charge movement. Okay, So I have an example here that I wanted to talk about closing, like I said, closing circuits. How do I close circuits to make sure charge can flow? So here's a two-way switch for a staircase light, and I borrowed this from Draw Yourself Smart Physics. It's a book I have, my sister gave me, page 31. And you can see that we have a couple of circuits here. I have a battery in both of them. This is the battery here. Right there is the battery. And notice that there's a long plate and a short plate. That is the symbol for a battery. So I can label this a plus and a minus, and a plus and a minus. So when current flows in this circuit, it will flow in the clockwise direction. Okay, so when we think about closed circuits, they will form a loop. And we can talk about that loop being a clockwise direction or a counterclockwise direction. So it says for a light over a staircase, there's a two-way switch at the bottom and another at the top. Okay, so I grew up with one of those. There was one at the bottom and one at the top, and you could turn on and off the light regardless of whether you were at the bottom of the stairs or the top of the stairs. So when you look at this circuit, which would you say is closed? Which diagram represents the light being on? Okay, so you need to have a closed circuit in order to have current flow and turn the light on. Well, we can see in situation B, there's an actual connection across here with the wires. It forms an actual loop, and so B is the answer. In A, we can see that there's spacing. There's no way for those charges to move in a closed loop. So A is not a closed circuit. Okay, so that's the fundamental about closing circuits. Circuits need to be closed to have a current flowing through the wire. So here's a couple more examples from Draw Yourself Smart. On page 74, they had this nice little circuit going on. There's a battery in here. You can see here's the positive plate and here's the negative plate. And so when I think about conventional current flowing, the current will flow up out of this branch and up into this branch. And we'll get into Kirchhoff's junction rule that says now we have two branches, right? But because the switch is here, I can either form a loop on this side, or when I pull the switch over to A, I could have a loop over on this side. So in this situation, they might ask, like, which of the light bulbs are lit in this situation? In this situation, let's follow the current. Does it follow a loop? So I can look here, it goes from B to D, and then when it gets to D, it sort of has a choice here. And let's go the easiest choice. Let's have it go downward. When it goes downward, I see it goes through G and then F and then back up to the battery again. So this is a closed loop right here. I can call this the closed loop, and I'll call this closed loop A. And in closed loop A, because this is a closed loop, I will have both F and G being lit. Okay, let's look at the other direction here where it went upward here. So the current comes here, comes to D, and it gets a choice to split. And this is like maybe hoses in your garden. When you have a hose splitter, it'll just split. It can do that. You'll have less current in each of those directions, and we'll get to Kirchhoff's junction rule, like I said, in another lesson. But so it'll go along here over to C. Okay, I'm okay with that. And then if it tries to go to A, But there's no circuit elements down here along A, so we don't really have to worry about that. It can also go downward at C, and I can see that it'll go through E and then back up for the battery. And that is another loop in our circuit. So it'll go like this around, and that can be loop B. So we can see in loop B that the light bulb E is also being lit up in this circuit. Okay, so that's how to follow a closed loop around. I might ask you when I close when I close switch A, which bells will ring in here. Well, you would follow the circuit around, okay? And let's say this is a positive side and a negative side. They don't put it on here, but you know batteries have a positive and negative side. And so when I think about current leaving this battery, it's the conventional current, and I'll follow it at this branch. And it has a choice to go along this branch. And if I close A, then I can get it to go along that branch. It'll definitely go in that direction. It'll come along to bell X, and then it'll come here. And then if B is open, the only way it can go is upward. Notice we have this situation where we have current going down a branch and going up a branch, and that's not possible. So if we close A only, there are no bells that are going to ring. None of them form a closed circuit. And I see what you're saying, like this is a loop, like geometrically this is a closed loop, but we need the current to form a closed loop, which means that the current needs to leave the positive side of the battery and then go back into the negative side of the battery. That battery has to be within, or whatever power supply you have in there, that power supply has to be in the loop of this current, or else there will be no current. So let's look at this here a little bit closer. I'll get rid of this and start over. If we want current to flow in this circuit, and let me put the positive and minus back in, we can get it to go in this direction. If we want current to flow, we have to close at least switch B so that the current can flow back into the negative side of the battery. So if I close switch B, I can get bell Y and bell Z to ring. Okay, so Y and Z. If I want to get bell X to ring, I can close A. So once I close A, so I'll put A and B, both switches have to be closed, then I can get X, Y, and Z to ring. So that's an example of closing circuits. You'll get more practice at this as we move towards circuit analysis. Okay? So now that you have an understanding of how currents work, let's get into quantifying the different physical things in current. Current is defined to be the time rate of flow of free charges, and this could be electrons or ions. Like I said, you could have positive charges moving someplace in a liquid or whatever. Electrophoresis, when you do maybe DNA, that definitely has a current through a liquid. So I'm not saying that only electrons flow, but we think about most often it's electrons flowing. So there's the change in charge over the change in time. I put these pictures over here. Notice that the direction of conventional current is in the direction of the positive flow. And in this situation down here, I like how they have the electric field. And notice that I've applied a voltage over here, right? Let me put a battery in here. Charges will flow to the negative plate, so I know that I can put a battery in here, and I'll have a positive on this side and a negative on that side, and the current will flow in a counterclockwise loop in this circuit that I made. Okay, if I put a battery down here, which direction would I need to make it go? Well, also the electric field is in this direction. The negative charges will move towards the positive plate of the battery, and we can see that the battery is in the same orientation down here as it is up here in order to get negative charges to flow. Okay, so we're looking for current is the amount of charges that flow through an area in a certain amount of time. Okay, so that's the definition. Units of current is a coulomb per second. Notice that, coulomb per second. But we honor ampere by having the units of amperes. And the shorthand for this is amp, and you may recognize this from everyday life working with current. Many instruments, technologies are rated with an ampage. What's the best and optimal or the maximum ampage for that device? And that may be where you recognize amps. So I wanted to do just a quick example of how to calculate current. I picked the defibrillator problem again. A defibrillator is used during a heart attack to restore the heart to its normal beating pattern. A defibrillator passes 18 amps of current through the torso of a person in 2 milliseconds. So I see a current, 18 amps, and I see a period of time, 2 milliseconds, which is 10 to the negative third seconds. Okay. It says how much charge moves in this time. Well, I'll do a quick step of algebra on this equation, and I can get that the amount of charge that passes in a certain amount of time is going to be the current times that time. So I can plug in what I know, 18 times 2 times 10 to the negative third. And when you multiply those two things together in your calculator, you get 0.036, and the units on that is going to be coulombs, right? It's a charge, so that's coulombs. So that's part A. Part B says how many electrons pass through the wires. So this may be a familiar task for you to figure out how many electrons is in that many coulombs. The number of electrons is going to be that amount of charge divided by the elementary charge. Okay, so I'm going to take 0.036 coulombs. And per electron, there is 1.6 times 10 to the negative 19th coulombs per electron. So that will give us the number of electrons. And when you run this through the calculator, you get 2.25 times 10 to the 17th electrons. So not quite a mole. We're not to a mole yet. But that would be the number of electrons that pass through that patient, through their nerves, through the body, through the heart, right? So that would be the number of electrons.